Okay, so a quick recap of what we did in the last week. So we talked a little about the problem of classification. And then the way it worked was we had an input space I, and then there were lots of data points, data samples from this input space I. So we called them all DI. And then we had a set of labels C, and each data point here was associated with a label. So for example, the data point, I don't know, 0 0.8, 0 0.5 was associated with the label red. The data point 0 0.2, 0 0.2 was associated with the label blue, etc., etc. So our goal was to create a function, to find a function f, that given a new data point that the algorithm has never seen, so let's say 0 0.5, 0 0.2, it is able to give to assign it a color, so a class, so either blue or red. And our hope was that this function here would be able to generalize, so it would be able to guess correctly for data that the algorithm has never seen. Okay, now the problem is that the way we did this was with nearest neighbors, so with the nearest neighbors classification, nearest neighbors algorithm. And this algorithm doesn't really learn anything. Like generally what we would expect is that the algorithm would take the training data and learn some patterns and do some calculations and get some knowledge out of the data somehow, extract some information from the data, do something with it. And what the nearest neighbors algorithm does is it just stores it. And then when you ask it what is the class of a new data sample that it has never seen, then it only then it looks at the entire data set and does something with it. So it is kind of like weird that it is too lazy when training, and it takes too much time when actually testing it. So in this class, in this week, we are gonna learn a little more about learning, about like we're gonna do actually some real learning. So to do this, I want to create a data set, a toy data set that we're gonna play with. So the idea is that this is a training set, and this is a test set. So there are like, I don't know, 14 points here in the training set and 4 points in the test set. And I created 4 columns here. So I created, I don't know, gender, mean pupil dilation, total reading time, and number of fixations. And this is like associated with reading. So gender is gender, but then pupil dilation, I don't know if you know how this works, but like when people read, you can measure the dilation of their pupil, of the eye. And you can also measure the total reading time, so the time they took to read something. And when we read, we make fixations on certain regions of the text. We don't actually read like our eyes don't go smoothly through the line. It jumps from places to places in the text. So these are called fixations. So what this here is like the number of fixations that a person does. Okay, so a disclaimer here needs to be said. I totally created this data by hand. Like this data is not real. Do not believe that this data reflects in any way reality. It doesn't. Don't think that men read faster or women read faster or men make more fixation than women or something. Like this is totally generated data, like fabricated data. This is not supposed to be taken seriously. Okay, given this disclaimer, the idea here is that there are some people who are male, there are some people who are female. We're gonna do some play a little with classification, I guess, in the future, like soon. But first, we are gonna actually look at the 2 middle columns. So what we actually are gonna do is to try to guess the total reading time given the mean pupil dilation. Okay, and this is what the task of regression is. So if you remember from classification that was just above here, we had an input space I and a set of labels C, and then our goal was to create a function that would take an element of the input space and output a label. So it would output a color in our case, or if the dog was a German Shepherd or a Chihuahua or another dog that I didn't manage to find a name for, or anything like cat or not cat, spam or not spam, etc. So in the case of regression, instead of having a class, we actually have a number. So we just need, this is the only difference. We don't have that part where we have like a set of classes. We only want our function to receive a new element and output a number. So it will output maybe it receives some numbers and it outputs another number here. So that's all. That's the only difference between regression and classification. So what I did was I took this data here and I decided to plot it. So basically I created a NumPy array with only the second and the third column. So the mean pupil dilation is the second column and total reading time is the third column. And then I print them, which is here. So I can have the vector here and you can see the other vector here. Like it's just a list. And then I made a plot here, and then you can see the plot here. So since I fabricated this data, since I was the one who created the data, I could just choose the values of these data points here, such that the mean pupil dilation kind of can be predicted based on, no, like the total reading time kind of can be predicted based on the mean pupil dilation, right? So like if you see a big number for mean pupil dilation, you would guess that the total reading time would be around here. If you see a small number for the mean pupil dilation, then you would guess that the total reading time is around here. So you can see that there is some sort of linear relationship between the mean pupil dilation and the total reading time. So if you are not really understanding this, I would suggest you to stop the video and look a little at this graph and think a little about how these two variables relate. So these are all these points here are the points that I had here, okay? So these are all data points. So whenever like I have a person here, for example, who has a small mean pupil dilation, then this person also has a relatively small number for the total reading time. Whenever I have a person here who has a big mean pupil dilation, he also has a big total reading time. So that's what I am plotting here. And then what we are going to try to do is we're going to use this training set to learn a representation such that then so this is the entire training set, okay? And then we had another test set. And in the test set there are other mean pupil dilation. So maybe there is a 0.65 here that we don't have in our training set. And then the question is, what should be the value for the total reading time when the mean pupil dilation is 0.65? And then what we're going to do is we're going to have a model that is going to be able to kind of like fit a line here. And then it will guess, oh, it is here. It should be here more or less. And then it's going to put the value here. And then we are going to compare if the value that the model gave is really the value that we got from the test set. That's it. Okay, but to be able to do this, I wanted to consider what we already know based on the points here that we have. So look at, for example, this point here, this one here. So when x equals 0.4, our y equals, I don't know, something that is close to 60. When x equals 0.39 or something like that, then y equals a value like 65, something like that. When x equals maybe 0.42, y equals 50 something. So we know already, like these dots here, they give us information about what should the y be when the x is a certain value, right? And I wanted to notice that any line can be described by an equation like this one, y equals ax plus b. So when x equals 0.4, this y here should be 0, it should be 60, I guess. And this way you go, like, I mean, when x equals a value, y equals another value. So, and then the a and the b here, they describe how the line is supposed to be. So the a actually tells how inclined the line is. So when a is 0, then the line is like this. When a is a very big number, then the line is like this. And the b actually tells if the line is here, or if the line is here, or if the line is like up here, or if the line is low. So anyway, it doesn't matter. But the point here is that a line can be described by these equation here. So what we can do is already to put those points, all our data points in here. So again, 0.4 here is when 0.4, when x equals 0.4, y is supposed to be 61. So it was 61. When x equals 0.44, which is, I guess, this one, or this one maybe. When x equals 0.44, then y equals 57. And this way you go. So you can put this all into a system of equations. Now, if you remember from school, when we create a system of equations like this, our goal is to find values for a and b such that whatever is for all equations, whatever is in the left can be the same as whatever is in the right. So I can be smart. I have to be smart, like, and to find a value for a and a value for b such that a times 0.39 plus b will be 66, and a times 0.4 plus b is going to be 61, and a 0.44 plus b equals 57. But okay, so what I wanted to get convinced here is that it doesn't matter which value I chose for a and b. There is no way for me to find a solution that respects all the equations at the same time. And the interpretation for this in this math here is that since ax plus b describes a line, then if you try to make a straight line in this graph, there is no way for me to create a straight line that will cross through all of these points here. Like, it will always be just a little off one point or another. So this means that there is no solution for this equation here, for this system of equations here. So, okay, so our goal was to find an a and a b that would solve this system of equations, and we just established that there is no way to solve this system of equations. So what can we do about this? So, I mean, yeah, there is no way to have a line that will cross through all the points, but there is a way to find a line that will be close enough to all the points, right? That will be like, I mean, if I create a line that crosses here, then probably this line is not a very good description of my data that is here, that is like far away from the line. So I can try to find a line that it remains as close as possible to all the points. So the line that minimizes the distance from the line to the points. So that is like, let's say that the line is going here and that it passes here when x equals, I don't know, 0.9, it is here. And then our goal is, let's say that the ideal line would pass here. So our goal is to have this distance here, like the distance between the line and this data point, this distance here, to be as small as possible. And we want also the distance between the line and this other data point to be as small as possible. And we want the distance between the line and this data point to also be as small as possible, and so on and so on. So we want the line to be as close as possible, or in other words, to have a distance as small as possible to these data points. So how do we do this? Well, we can like include into this system of equations an error variable. So this error variable is that distance that I was showing you. So let's take this thing here, for example. 66 equals A times 0.39 plus B plus E1. So 0.9 plus B plus 0.9, A times 0.39 plus B is like, okay, like 0.39 is here, so the A times, and we want it to, and this point is the 66, right? And actually this point is the 66. So 0.39 is here, and this point is 66. But we know that the line will probably not cross here. It will probably cross a little below because like of the way the data is. So probably it will be here. So A times 0.39 plus B, which is like the right side of the equation, is going to be here, which is the line. And then when if I am here and I sum some value, like I sum an error value, I can go here. I can like push the y, which is here. I can push the y value a little up, and I get to this point here. So this bumping is this error value here. So, and we can include an error value in each one of our equations. Now, it doesn't matter which A and which B I choose, there is always a possible error value that makes this equation here, that makes all of these equations satisfiable. I can always, so let's say that this value here sums to 40, then I can sum 26 here, and then the entire first equation is correct. Let's say that this other one here sums to, I don't know, 37 or whatever, like 80, then I can find, so if it is 80, then I can find an E2 that is minus 19, which would cause this entire equation here to be true. So there is always a value of epsilon here, like of each one of these epsilons here, that if I whatever is the value of this side, this part of the equation, like whatever is the sum here, if I sum this epsilon, I can cause this entire equation to get satisfied. So this system of equations is solvable. And our goal is, remember, like these epsilons here are the distance between the actual points and our line, our ideal line. So our goal here is to make this epsilon here as small as possible, because this means the error is as small as possible. So to do this, I will just get out of this idea of equations, systems of equations, which is something that it's like it was very nice to play with in school, but it is very inefficient to calculate this like by hand, the way we did in school. Maybe there is like a better way would be to represent these as matrices. So I can have an A that is multiplied, so a multiplication of a scalar A with a matrix is a multiplication of each one of the values of the scalar into the matrix. So like, let's say that A is 2, so this would multiply the entire values here of the matrix by 2. So we can then, since this thing is a scalar, this thing is a number, and this thing is a number, and this thing it could be represented as a vector. So we can, this system of equations here is easily like transformable into this other system, into this other equation here. Only this equation is like a linear algebra thing. And then if we consider this our x, and this our epsilon, and this our y, then this entire thing can be translated into this very short way here. And then, so a note about notation. I am using bold letters whenever I have a matrix, and I'm using, I don't know, normal, non-bold letters whenever I have a scalar. So this will be, I hope that this is useful for you to guess, to know, okay, this is a number, like this, a scalar is a number, okay? So this is a number, and this is a bold letter, so it is a matrix. Okay, so what are we gonna do now is the following. So these epsilons here as you remember, they are my error here. So given the line, like if the line passes here, then it is this distance between the line and the actual point that was observed. So, and my goal is to minimize these errors, is to make these errors as small as possible. So my goal is to make each one of these epsilons here as small as possible. So the way it works is when you do regression, when you do classification too, but like in our case here, when you do regression, you want to minimize a cost function, a loss function. So these are the two words that are used, either loss or cost function. And in our case here, our cost function is something that, like, it's something that integrates all of these values here. So there can be several types of cost functions. So we are going to take a look at some of them. Okay, so the first one that I want to show you is the naive option, which is just like to sum each one of the epsilons. So here it's the sum for each I of all the epsilon I. So this means it's just to sum all the epsilons. Now, the problem with this approach is that some epsilons may be positive and some epsilons may be negative. So in this case, if the line crosses here, positive epsilons would be epsilons that cause a bump forward, like up. Like, so this distance here would be a positive distance. And then this distance here, if the line is crossing here, this distance between the line and this point here, which is like the point is below the line, this would be a negative error. So if I sum, maybe like points that are below may compensate the points that are above the line. So this is exemplified in this example here. So let's say that my data set is actually different. It has like 5 points like that go in a line and a point like this one here. So ignore the blue line. Just think of the points, like each one of the red points and this point here too. So these are, let's say that my data set is composed of 6 data points, and these are the data points. So the point 1, 2, the point 2, 3, the point 3, 4, the point 4, 5, the point 5, 6, and the point 6, 1. So if I just sum all the errors, then this line here would have error 0. This line here it passes exactly 1 unit below each one of these points. So it is like the error here is 1, 2, 3, 4, 5, but then it passes 5 units above this point. So like the error here is -5. And if I sum -5 with the 5 ones here, then I end up having error 0. So probably this cost function here is not really a good cost function, right? Because it's not producing a line that is good. Like, it's producing a line that is very strange. So one way in which you can try to solve this is by saying, okay, I don't care if the point is above or below the line. It doesn't matter. I can call this error here counts as 1, this error counts as 1, and this error doesn't need to count as -5, it can only count as 5. So I would sum all of the errors independent of if they are below or above. So it means, so this is represented by this equation here. So this is the way you normally say. So there are 3 ways in which you can write this. You can say that this loss is the L1 norm. So this is just the name of this kind of function where you go, it is either above or below, like either above or below. You don't care about the sign, you just sum all the differences between the point and the line. So this is called L1 norm, which is the sum for each one of the i's, where I is each one of these errors here, of the module of the I. So this function here is the the function that removes the sign. You just care about the magnitude of the point that is inside, which is also the same as the L1 norm of this vector. So this is one way of notating it, of writing it. So this would solve the problem, but there is only one very very small detail, which is when the error here gets to 0, then the module function is actually, this module function here is actually not continuous when the error is 0, which is like, so this is a calculus thing that I don't want to go much into the details, but the function is just not continuous when this sum here equals 0. And then this means that the derivative of the function doesn't exist at that exact point. And then for this reason, instead of just like getting the module, like just getting the magnitude, we square the value. So it's the sum of the squared errors. And this is just a trick that makes the function continue when x equals 0. And this will help us in the future on, like, for us to minimize this function. So this function is continuous in all other points, but only when this sum here equals 0, then it's not continuous. So this is the important part. So, okay, so we now found that we want to minimize this function here. We want to minimize the sum of squared errors. So let's say, for example, let's go back to our plot here. Let's imagine that there is a line here. What we want to do is, let's say that the line passes here. There is this distance here between the line and the point. So we take this distance, we square this distance, then it's going to be positive. And then we take this other distance here, we square, it's going to be positive too. Then we take this other distance, we square, it's going to be positive. Then we take this other distance, we square, it's going to be positive. And then we sum all of them. We sum the square distance here with the square distance here, with the square distance here, with the square distance here. We sum all of these distances. This is the thing that we want to minimize. We want to find an A and a B, like here. We want to find an A and a B, such that all of these errors here are as small as possible, or actually such that the sum of all of these elements here is squared. So like the sum of these elements squared with these elements squared with these elements squared with these elements squared is as small as possible. And then to find this sum, we're gonna use a method called gradient descent. Okay, so gradient descent is going to depend on the derivative of the function, which is of this function here, the sum of the squared errors. So I will finish this video here, and then in the next video we are going to talk a little about gradient descent and how it works.